All right, so we're going to talk a little bit about some review stuff. So things we need to know to remember in order to do the rest of this. So remember, equation of a line, you need point, and you need a slope. And if you want to write the equation of a line through a point with this slope, you can just use point slope form. That's all good. Okay, so point slope form, y minus y1 equals m times x minus x1. So I'm going to change that to a plus because minus a negative. Also, so this is a geometry, remembering a secant line is a line that intersects a curve twice, or in 2 points. Okay, so if I want to draw the secant line for this funny looking, it looks like a cubic from P to Q, it would go and we'd go through there. It actually, if you keep going, it hits it 3 times, but if we're talking about the secant line from P to Q, there it is. All right, now, what if we go back to our fruit fly problem that we were talking about earlier, and we want to find the rate of change on a particular day? Well, we only know how to find slope or rate of change between 2 points, so we are going to use that idea. Well, we could found it between P and Q, all right? And here it is, okay, right there, 8.6, all right? We did that already. And if I move that a little closer, so I move the Q and I say, let's go to 40 days, between 23 and 40 days, it's a little bit steeper. And here's the slope, it's over here in this table. We'll call that point X. Okay, so that's between P and X. What if I move it a little closer? Between P and Y, well, there's that slope. Look at how it's changing, 8.6, 10.6, 13.3, and then what if I go to B, which is already marked on our picture, and now it's 16.4. Now, it looks like if I want to draw the slope right at that point, it's something like this. So we're getting closer and closer and closer to the actual tangent line, or the actual rate of change, just at day 23, at day P, where that point is. So we're going to use the concept of limit to see if we can get that exact tangent line rather than just a secant line, because we don't, in a tangent line, you only have 1 point. So that brings us to the next concept. We have to talk about tangent lines, which actually tell us instantaneous rate of change right at that minute, second, hour, day, whatever your time is. Okay, so remember, for a circle, it intersects a tangent line, intersects the circle in 1 point. It's called the point of tangency. Boy, is that terrible handwriting on this thing. And it is also perpendicular to the radius at that point of tangency, okay? So that's what it is on a circle. On a curve, it's very similar. It's not quite exactly the same. It goes through, it hits it at that 1 point. It doesn't have a radius to be perpendicular to, but it has something called a normal line that it's perpendicular to. Now, unlike in a circle, a tangent line on a curve might actually hit the curve in 2 places. That's a bad line, so I'm going to try that again. So if I'm talking about my tangent line at point P on this one, it looks like there, but see, it does end up hitting down here. That's okay. Locally, it is a tangent line. It's just that because it's not a circle and round, it curves back up, it's going to hit it again. Actually, it'll hit it again up here if I keep going, right? So locally, it's a tangent line. So it might hit another point. It might even cross through the curve at the point P. That is when P is an inflection point where the curve changes from concave up to concave down, or concave down to concave up in our particular instance. And we're going to talk more about how you find exact inflection points. That's part of what we're going to do in calculus. But it is possible for a tangent line to cross through. All right, so normal line, something you need to know. This book covers it a lot. A normal line is a line perpendicular to a curve. All right, and we often talk about the perpendicular to the tangent at the point of tangency. So that line that I drew there is the normal line up in this parabola. So that's a normal line. Some people call it an orthogonal line. Both of those words are just fancy math words for perpendicular. All right, so we're going to talk about how to find the slope of a secant line and then use it to help us find the slope of the line at an individual point. So we're going to use the concept of a limit to do that. So we're going to talk about point P, and we're going to try to find the slope of the tangent line at point P. Now, you notice I've drawn in a secant line from P to Q. We're going to use that concept and use that slope of a secant line to find that. Now, so we're going to call this point X, right? So that means that would have coordinates X, comma, f of X, all right? Now, this other guy, we're going to actually change this to an H, this delta X. You notice that you will see that on the AP test, those of you who are taking it, but our book uses H, just so we look like what the book does at the moment, we'll do that. So this other point up here then, if that little distance is H, we go all the way out to X plus H, right? X plus H. And then up here, we'd find that by substituting X plus H in, so we get F of X plus H for that y coordinate. So that one would be X plus H, comma, F of X plus H. All right, so we have some weird looking coordinates, but if we want to go back and find slope, then slope would be F of X plus H, y2, minus y1 F of X, all over x2 minus x1. All right, so if we simplify the bottom, notice that those x's cancel out and we just get H. And so let's think about what happens if we start moving this Q a little closer and make H half as small, then a quarter as small, and then a little bit smaller, and so that we're getting closer and closer and closer, we end up actually getting to the actual tangent line, so half, and then quarter, and then what if H is getting closer and closer to 0, in other words, a limit. So if we found the limit as H goes to 0 of that whole slope, we're actually finding the slope of the tangent line. Okay, over H because we canceled those x's out. So that is the slope of the curve at the point, or the slope of the tangent line. Also known as instantaneous rate of change. All right, so there we go. Now, let's do some examples.